In this video, we're going to look at discrete numeric probability distributions. And this video is just going to be a brief overview of the three most common discrete numeric probability distributions and what we mean by discrete numeric probability distributions. And the three distributions we're going to talk about are called the binomial, the hypergeometric, and the Poisson. And these three common discrete numeric probability distributions, what we can imagine is something random is going on. We're doing some kind of random experiment. And the outcome of the experiment is going to be to count something. So we're going to be counting up how many of something occur at the end. So discrete means that the outcome is going to be a number that is not continuous. So it's going to be numeric, and it's going to be something that we count up at the end. So what does discrete mean? Now later we're going to cover continuous distributions. The best example I have that I think can give you an idea of the difference between discrete and continuous is the difference between your shoe size and the length of your foot. Now something like your shoe size is discrete. Now in the United States, we do shoe sizes like the following. A very small shoe size might be a 4, and the next shoe size would be a 4.5, and then the next shoe size would be a 5, and then 5.5, and then 6, and then 6.5. What's happening to your shoe size as your foot grows is your shoe size is jumping from 4 to 4.5. Your shoe size doesn't go in between those numbers. It's either 4 or it's 4.5, but nothing in between. So you know that you're dealing with something that is a discrete outcome if there are gaps in between the numerical possibilities. That's what we mean by discrete. Let me tell you what discrete doesn't mean. Some people assume that because it's discrete, I'm listing these shoe sizes here. Some people assume, sorry, that should be 6.5. Some people assume that discrete is the same thing as finite, but it's not. Discrete is not the same thing as finite. Now, you might have a discrete variable where there are a finite number of outcomes, but you can also have a discrete outcome where the number of possibilities is infinite. For example, we could use a discrete sort of distribution to describe the number of grains of sand on a beach, or the number of snowflakes that fall, or the number of raindrops that fall. Anything that we can count is discrete, even if it's infinite. Now, continuous, the number of outcomes, the number of possibilities for something that's continuous are necessarily infinite. And in mathematics, we say something that's continuous is uncountably infinite. You can't even begin to count up how many possibilities there are. You can't even begin to list the possibilities either. For example, with your length of your foot, in inches, the length of someone's foot might be 3 inches. What's the next possibility if we were to make a list? Okay, 3.1 inches. But wait, there's no gap, right? We can't have gaps between the possibilities if something is continuous. By making this list starting with 3 and the next possibility being 3.1, you can see that I have already omitted an infinite number of possibilities. Even if I make the next possibility this, I have still omitted an infinite number of possibilities between 3 and 3.0000001 inches, because we can measure something that's continuous as precisely as we want. So things that might be continuous could be the amount of liquid, the volume of liquid in a container, or the length of anything, or the temperature of anything, would all be examples of things that are continuous. Now we have to model, we have to discuss these two types of outcomes differently. Discrete and continuous, we have to model differently, because if something is discrete, I can at least in principle make a list of all the possibilities, even if there's an infinite number. So I can talk about the probability that someone has a shoe size of 4. Or we can talk about the probability that there are 1,389,462 grains of sand on a beach, or that many raindrops fall during a 1-minute period in a certain area. But we cannot really talk about the probability that someone's foot is exactly 3 inches long, or exactly all these zeros and 1 inches long, because there are uncountably infinite numbers of possibilities here. The probability of any one particular number, whether it's 3 inches or whether it's 3.2 inches or whether it's pi inches, is going to be 0. Because with an uncountably infinite number of possibilities, the probability has to be evenly smeared over an uncountably infinite number of possibilities. You can't assign a positive number to any one possibility for a continuous probability. So we're focused now on discrete numeric probability distributions. And the outcomes here are always going to be counting things up. So how many possibilities are there? So let's look at the basic properties of these most common probability distributions, and then I'll do a separate video on each one. So briefly speaking, the Poisson distribution is usually when we're talking about modeling arrivals, or during a certain time period, how many times does something happen? So an example might be, given an average rate of any kind of occurrence, we call mu per unit of time, we calculate the probability that x, 0, 1, 2, or 3, events occur in that specific unit of time. And we talk about independent arrivals. These things that are happening over time happen independently. So, practical example might be, suppose there are 2.78 accidents per month at an intersection using historical data. Then we might want to know, what's the probability there are no accidents this month? What's the probability there's 1 accident? Or what's the probability there are 10 accidents? Exactly 10. Not 10 or less, not 10 or more, but we want to know the probability that there are 10 accidents this month. Or even 100,000 accidents. It's possible. It might be extremely unlikely that we have 100,000 accidents, but it's theoretically possible that we could have that number. Now, if these accidents occur independently, which means that given the fact that there was already an accident today, that does not affect the probability that there's another accident today, it doesn't increase or decrease it, then we can use the Poisson distribution in order to calculate the probability of any number of accidents. And so we will look at that in a separate video. The two other most common discrete numeric probability distributions are the binomial and the hypergeometric. And I like to consider these two together because it seems like these two are more closely related to each other than they are to the Poisson. The binomial distribution and the hypergeometric, you can think about the difference between them one of two ways. First way you can compare them is you can say, well, suppose we have a population of items, whether it's a bucket of balls or cards or people, and we're going to sample n of them, 5 of them or 10 of them from the population, and we want to know what the probability is that x of them, 0, 1, or 2, or 3, so x of the n that we sample are of a certain type, which we're going to call a success. So for example, we might have a bucket full of balls, and some of them are black and some of them are white. And out of this bucket of balls, we're going to select 5 balls. And we want to know, what is the probability that 2 of the 5 are white balls? That's a perfect example of what we could be doing here. Now, the big difference between these two distributions, the binomial and the hypergeometric, is that with the binomial, what we're assuming is that we're sampling one ball out of the bucket at a time, and then we replace the sampled one, mix the balls back up, and then we sample the second one. So we replace the sampled unit before randomly selecting the next one. But in the hypergeometric, we pull a ball out, and then we pull a second ball out, and a third ball, and a fourth ball, and a fifth ball, all at the same time, without replacing the sampled units. So sometimes people describe the binomial and the hypergeometric, the difference as the binomial you're sampling with replacement, and the hypergeometric you're sampling without replacement. Now what's the big difference here? Well, the difference is in the binomial situation, if you pull out a ball, replace it, mix the balls up again, before you pull the second ball out, what you're doing is you're keeping the probabilities the same. Each time you pull a ball out, you replace it. So you're not changing the number of white and black balls in the bucket. So you're keeping the probabilities the same. Every time you draw, it's exactly the same as the last time you drew a ball out. With the hypergeometric, that's not true. Because if you take a ball out, you are changing the probability that the next one is a black or a white ball. Suppose you pull a white ball out. Well, that's going to lower the probability that the next ball could be a white ball, because there's one less white ball in the bucket now. So that's the big difference between the two. Now, alternatively, the way I prefer to think about the binomial and the hypergeometric, it doesn't mean that one's right and one's wrong, but you can think about the binomial as being used when you are doing several things, and each time you repeat this thing you're doing is independent and identical. So each trial, each time you pull a ball out of the bucket, for example, is independent and identical of the last time that you did it. So for example, you can think about flipping coins. Each time you flip a coin is independent of the last time you flipped a coin. Each time you roll a die is independent, meaning that the probability of a 6 this time does not depend on whether it was a 6 the last time. And the hypergeometric is used when the trials are dependent. The probability of pulling a white ball out this time depends on whether the last ball I pulled out of the bucket was white, as long as I'm not replacing them, you see. So the hypergeometric is very often used for card probabilities. You have a deck of 52 cards, and you want to know what the probability is of getting a queen, for example. Well, if I'm dealing 5 cards to you out of a deck, I'm not replacing those cards. And each time I deal you a card, the probability that that one is a queen is changing based on whether the last one was a queen or not. And so the hypergeometric deals with dependent trials. The binomial is used with independent trials. So in the next video, we're going to look at the Poisson, and then in the video following, we'll look at the binomial, and then the one after that, we'll look at the hypergeometric and how these formulas actually work.